We're going to start with Chapter 9. We're going to expand our understanding of electrical circuits from Chapter 18. You should download the Chapter 19 objectives. They're on the LMS under Monday's page for March 23rd. We're going to notice there are only 3 objectives, but it's still quite extensive what we're going to do. We're going to start with Objective 1, which deals with what is known as series and parallel circuits. You should also, this should be downloaded in Notability. You should also download the notes packet. You can download it into Notability. You can take notes in Notability, or you can print it out as a hard copy and take notes on that. Either way is fine. We're going to start. This is called EMF and terminal voltage. To produce the current, a battery, these are 2 different batteries. This is a 9-volt battery. This is a 1.5 volt battery. Basically what a battery does is it has a positive terminal, which is, we call that high potential, and a negative terminal, a positive terminal, which is that high potential, and a negative terminal, which is that low potential. This is the positive terminal of this battery and the negative terminal of this. What happens when you connect them together, like pouring water, you have a bucket in your hand, pouring water out onto the ground, the bucket's at high potential, the ground's at low potential. When we connect these together, the current goes from high to low potential. But we know that what actually happening in electrons are going from negative to positive terminal. But we always talk about it in terms of high potential to low potential. Okay? So a battery is used to produce a current, or you can have a power supply or some type of electric generator. Basically, it transfers one type of energy, for a battery is chemical energy, into electrical energy. Such a device is called a source or electromotive force. It provides some type of electric type of force to the electrons in this device that causes them to move through the wires or the devices that are in the equipment. Electromotive force is abbreviated EMF. The EMF, or potential difference, or voltage, all those mean basically the same thing, but the EMF is when there's no current flowing through the battery at all. So it's a very specific type of voltage, but it's a very specific type of voltage when there's no current flowing through the battery. The abbreviation for EMF is the Greek letter capital epsilon. A battery does not produce a constant current, but it does produce a constant voltage. That's the key to the battery. For any battery, there's an internal resistance to the flow of charge, because in order for this charge to flow, there's actually a chemical reaction occurring in this battery. And that chemical reaction does not occur instantaneously. It takes time, so that's called the resistance to this flow of current in the battery. An actual better model of a battery would be a resistor in series with a perfect EMF, or a perfect voltage source. So let's take a look at this and see how that works. So we're going to have, this is like a battery. This is, say that's one terminal of the battery, and that's the other terminal of the battery. We'll call this the positive terminal. We'll call this the negative terminal. This is, we'll say, point A, and this is point B. What this actually is, you can think of it as a circuit diagram. There's a very small resistor in this battery. We're going to call this lowercase r. Whoops, sorry. And there is a potential, or a battery. That's the symbol for a battery. That's the potential source. We're going across that. But instead of V, we use the symbol EMF, because this is the EMF when there's no current flowing through that battery. What we call this lowercase r is the internal resistance causes a voltage drop from A to B due to the current flow through these resistors. So this is at high potential to that low potential that causes the current to flow through that resistor and then through that EMF. Now, the equation that's used to represent this is that there is a potential drop between A and B. We call that potential A and B. This is at high potential, this is at low potential. That's equal to the EMF. But because this resistor causes a drop in the voltage, then this voltage that we get across these 2 points here is actually reduced by the voltage drop across that resistor. And we call that IR. According to Ohm's law, V equals IR. Remember, V equals IR is Ohm's law. And we use a lowercase r to represent an internal resistance instead of a capital R. So this EMF of this battery, when there's no current, is actually reduced by a small amount based on the voltage drop across that resistor. Right? Remember, this is a voltage drop. These are all voltages. And this is the voltage drop within the battery. All right? So let's see how this works a little bit. A little quick example problem. We have a 12-volt battery that has an internal resistance of 0.1 ohms. What is the terminal voltage when 10 amps of current are flowing through it? So this is what we have. This is the battery. This is the voltage battery when there's no current. So that's the EMF. 12 volts. We know the internal resistance of the battery. Instead of using capital R, we use a lowercase r. They mean the same thing, but internal resistance is usually written with a lowercase r. That's 0.1 ohms. The voltage between A and B is what we're trying to solve for. We have the current flowing through that battery of 10 amps. Again, the equation that we have is this one right here. This is the voltage drop due to the internal resistance of a battery. So the voltage between points A and B is equal to the EMF minus I times the internal resistance. We're trying to solve for this voltage that the battery is actually going to produce when a current of 10 amps is flowing through it. So the voltage between points A and B, sometimes we just leave the A, B off because we know the voltage drop is always between 2 points. So the EMF is 12 volts minus the current, which is 10 amps, times the internal resistance of 0.1 ohms. So we actually get a usable voltage in that battery to be 11 volts. Let's take a look if we actually have this battery in a circuit. So we have a 65 ohm resistor connected to the terminals of a battery whose EMF is 12 volts. Whose internal resistance is 0.5 ohms. The way we draw this circuit, we have a battery, two parallel lines, one shorter than the other, and there is an internal resistance. We usually draw the internal resistance real close to the battery, label that R, and we know what that internal resistance is. That internal resistance is 0.5 ohms. The EMF of the battery is given as 12.0 volts. This whole thing, I'm going to put a little circle around it. This whole thing is the battery. That battery is connected across a resistor, kind of like what we had in the lab that we did for Ohm's law. We had a power supply. This is the power supply. This is a resistor. This resistor is 65.0 ohms. And the first thing we want to do is determine the current going through this circuit. Since there's only one path for the current to travel through, there's only one current. Now, let's see what information we have. So, we want to solve for the current. Now, we know that this is the EMF and this is the internal resistance. From that information, we know that E minus IR is equal to the voltage drop. Now, I'm going to put a point A here and a point B here. This is a voltage drop across that resistor, but notice this point A is along the same path. So this has the same voltage drop. This is point A and this is point A. These are both the same point. This is point B. These are both the same point. In other words, this is all the same potential and this is all the same potential. So this voltage right here, remember Ohm's law, is V equals IR. So this potential drop across this resistor is, according to Ohm's law, IR. So for this equation, we put EMF is equal to I times internal resistance must be equal to IR. Again, this is the voltage drop across that resistor, which is equal to the voltage drop across this battery. They're the same thing. So let's see what we have. We want to determine the current. Since I have current here and current here, I'm going to put the current on the same side of the equation. I'm going to take negative IR, put on this side. So the EMF is equal to, this is an R, I times R plus I times internal resistance. This R is resistor outside the circuit. This R is the internal resistance. So then we put in, I can simplify this a little bit. I can put EMF, factor out that I, is I times R plus R. I'm going to solve for this current, so now I have 12.0 volts equal to current. Resistance outside the circuit, outside the battery, is 65.0 ohms plus the internal resistance, 0.5 ohms. Notice in this circuit there's only one path for the current to go, and notice what happens to resistance. The resistance is added together. We're going to see that again coming up in other types of circuits. So this current is going to be 0.183 amps. The current going through that circuit is the current going through the resistor, and is the current going through the battery and that internal resistance. And then part B, determine the terminal voltage of the battery, which is the voltage across AB, either across this AB or this AB is the same thing. Remember, the terminal voltage AB equal to EMF minus IR. It's actually the voltage that's going to be produced by this battery, and it's the voltage that's across that resistor. So then we have this voltage AB. The EMF is 12.0 volts minus a current, which is 0.183 amps. We just solved for that, times this internal resistance, which is 0.5 ohms. We get the voltage that's actually produced by the battery that goes across this resistor. We get that to be 11.9 volts. Notice it's not a real big drop, and it shouldn't be a real big drop. Most batteries don't have large internal resistances, and we hope not, because we want to get as much voltage out of that battery as we can. The next part, we want to determine the power dissipated in the resistor R. So this is the power. This is since it's capital R, we want the resistance, the power dissipated by this resistor right here. And the power determined by that resistor right there. We have a power equation. Power, right here, power resistance R is equal to I squared times R. Well, we know the current going through this resistor. That current is 0.183 amps. We know the value of that resistor is 65 ohms, so this is the power in resistor R. The current is 0.183 amps. That resistance, 65.0 ohms. We get that power to be 2.18 watts. We could also determine the power in the internal resistance. Again, the current is the same, but what's different is the resistor inside the battery. So the power for the internal resistance, the current is still 0.183 amps. Don't forget to square that. Sorry, this is square. Times the internal resistance, which is 0.5 ohms. Power of that internal resistance, or the battery itself, is 0.017 watts. Don't forget to square that power. All right, let's continue to series and parallel circuits. We're going to start with series circuits. So resistors connected end to end are said to be connected in series. To draw that simple series circuit, this is a battery. We have a wire connected to one resistor, connected to another resistor, and connected to another resistor. These are all connected by wires to the battery. We're going to call this the voltage, potential difference. We'll call this R1, this one R2, and this one R3. The current goes from high potential to low potential, because this is the high potential side of the battery, this is the low or negative potential side of the battery. And if we want to measure the voltage across each one, remember in the old law lab that we had, we put the two clips for the voltmeter across the resistor. So this is going to be the voltage across resistor 1. This is going to be the voltage across resistor 2. These are just meters that we're going to put across each resistor to measure the voltage drop across each one. This is the voltage drop across R3. Now, let's take a look at some of this information. Any charge that passes through R1, so any current or charge that passes through R1 must also pass through R2 and must also pass through R3. So any current flowing through R1 must go through R2 and R3 and back to the battery. Therefore, it's a little therefore sign, the current is constant in a series circuit because there's only one path for the current to go. So it's constant. Now let's take a look at how this relates to equations in Ohm's law. So the total current, this is the total current. And this current flows through R1, so it's equal to the current going through resistor 1. It also goes through R2, so that's the same current that goes through this resistor 2, the same current that goes through resistor 3. So this total current is the same as the current goes through all those resistors. Now, let's take a look at the voltage. The total voltage going from this point to this point. There's a voltage drop going across R1, V1. It's just like going down a set of steps. If you have a staircase that's three steps tall, this is one step, this is another step, and this is another step. You can think of a slinky going down those 3 steps because step 1 is higher than step 2, that slinky can go down. Step 2 is higher than step 3, it can go down, and step 3 it goes all the way down to the ground. So you have a slinky going down each of these. But if you measure the height of all 3 steps together, the total height is the height of this step, plus the height of this step, plus the height of this step. That height is analogous to the potential or the voltage across each one. So the total voltage is equal to the voltage across resistor 1, plus the voltage across resistor 2, plus the voltage across resistor 3. Now remember, we have Ohm's law, V equals IR. Let's take a look. This voltage right here, the total voltage, is equal to I times R1 plus I times R2 plus I times R3. Notice the I's are all the same, they're constant. I can factor out the I and get the total voltage is equal to I times R1 plus R2 plus R3. Notice all 3 of those resistors add up to be what we call the equivalent resistance. That's EQ, REQ, equivalent resistance. So then, the equivalent resistance for series circuits is R1 plus R2 plus R3. And the total voltage is I times equivalent resistance. So for a series circuit, we have these 3 main equations. Currents are equal. The voltage is summative. And the resistors are summative. Those are the 3 equations that relate resistors in series. Now let's go to a different type of circuit. Called a parallel circuit. Resistors arranged so the current is split into separate branches are said to be in parallel. Now let's take a look. We're going to have 3 resistors again, just like we had in series. We're going to have a battery, and then a wire is going to be connected to 3 resistors, except these 3 resistors are going to be in parallel. We're going to have this current branch, or this wire branch, into 3 different branches, or sections. We're going to put 1 resistor up here, 1 resistor in the middle, and run 1 resistor at the bottom. And we connect them all, and we connect this to the battery. Again, this is the battery. The current is flowing this way, which is the total current coming out of the battery. Once this current reaches this node or junction or point, it's called several different ways, this current branches into a current up here. We're going to call this I1. We'll call this resistor 1, resistor 2, and resistor 3. The current goes through this branch. We're going to call this I2. And we have a current coming through this branch, which we'll call I3. Now notice, each of these resistors are connected to this point, and this point is connected to this terminal of the battery. So all three of the left sides of these resistors are the same potential as this side of the battery. All three of these sides of the right side of the resistor are connected to this node or point, and that is connected to this side of the battery. So basically the voltage across each resistor is the same as the voltage drop across the battery. Is constant or the same as the battery. But that's not true of the current. The current is not the same. So what happens is this total current comes into this point, branches into current 1, current 2, and current 3. Then all three of those currents reach back here at this point, and they all come back together and form the total current again. So the total current entering the parallel branch, which is at this point right here, must be the same as the sum of the individual currents. Let's take a look. Some of the notes for equations for resistors in parallel. We just said that the total voltage is equal to the voltage across resistor 1 equal to voltage across resistor 2, which is equal to voltage across resistor 3. So in parallel circuits, the voltage is constant. And we said that the total current is summative. The total current going in here must be equal to the current going through resistor 1 plus the current going through resistor 2 plus the current going through resistor 3. Now let's take a look at, let's use the current equation. And remember Ohm's law, V equals IR. We solve this for I, we get V over R is equal to the current. So for this total current, it's going to be the total voltage over the equivalent resistance, which is the total resistance of everything. I1 is going to be the voltage across resistor 1 over resistor 1 plus V2 over R2 plus V3 over R3. But remember, these voltages are constant. The total voltage, V1, V2, V3 are all three the same. So I'm going to simplify this. I'm going to factor the voltages out because these are all the same voltages. So I'm going to get total voltage over equivalent resistance is equal to the voltage times 1 over R1 plus 1 over R2 plus 1 over R3. And total voltage is equal to this voltage, so the voltage cancels out. So what we have is this equation, 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. This is the equation for the equivalent resistance. So now, for parallel circuits, we have three significant equations. We have the voltage equation, where the voltages are constant, the current equation, where the total current is equal to the sum of the currents, and the equivalent resistance equation, where 1 over the equivalent resistance is equal to the sum of the inverse of each individual resistor. We're going to stop there with the notes. The next video is going to be doing some example problems. I'm going to stop there with